Good morning, guys. So last time we stopped somewhere here on the formula um, presented on the ACI code or even in the NSCP. So this is actually section 12.2.2 and 12.2.3. So the two formula uh, actually are just the same. The only difference that for section 12.2.2, the equations are actually simplified in a table wherein the values of your factor psi s, which is the reinforcement size factor, is actually included uh, in the derivation of the equation. So the formula was actually made into a more compact form, and also since the spacing and covering are um, specified, the value of your Cb plus Ktr over dV, which is present in 12.2.3, was actually deleted or removed in section 12.2.2. But if you understand the use of the formula 12.2.3, there's no problem, and you don't need to use formula, the tabulated formula in section 12.2.2. Okay, so today we're going to discuss more on what are the parameters involved here in formula 12.2.3 for us to be able to understand the use of it. Okay, so in this equation 12-1 has actually several factors or parameters involved. So the parameters in the numerator, except of course for Fy and F prime C, are a little bit new to us, and also the factor involving the denominator, lambda, Cb, Ktr, are actually uh, maybe new to us in this particular point. No? So we have to discuss what are these factors. By the way, the formula presented is actually in English units. So later on, I will show you how to convert it into a metric in case you need to solve the problem in SI or in the metric units. Okay. So let's start with the psi factors. We have actually three factors on psi. The first one is the psi t, which stands for the reinforcement location factor. Your psi e, which stands for the coating factor. And your psi s, which stands for your reinforcement size factor. So for the location factor, we only have two options, and that is option top and option other. Okay, so what does this reinforcement location factor gives us? Okay, so if you have a beam, say a rectangular beam here, if we have bars at the top, at the middle, somewhere at the middle, and somewhere at the bottom, we have to make a distinction whether the location of such reinforcement are considered on the top locations or top bar or other bars. Okay, so we only have two choices to make. We don't have any bottom bar here, and this is only applies, of course, with the length of development concept. In other situations, this may not apply. Okay, what's a top bar now? A top bar is a reinforcement which is placed at a location where at least 12 inches of concrete, okay, 12 inches thickness of concrete is cast below it. Okay, so the definition for a top reinforcement is that 12-inch thick of concrete is cast or is present, no, below the bar. Okay, so if we have here in our drawing three bars, this layer of bars, which involves, of course, three reinforcement, we are now talking of the amount of concrete which is present below it. Okay, so we have to measure at the bottom of this bar up to this part here. So this measurement should be at least what? According to the definition, it should be at least 12 inches or more. Okay, so when this distance is at least 12 inches or more, then the bars are top bars. Okay, we also have to measure this. If there is 12 inches or more, okay, at least 12 inches, greater or equal, you can specify. Of course, this part here, since it's very near to your bottom surface, therefore this is automatically uh, tagged. Okay, this is automatically considered as a bottom, sorry, an other bar. There's no word bottom here. Okay, so this is now a top bar if there is at least 12 inches or more of concrete placed below it. Okay, so that's definition of our uh, a top bar requirement. And if it is not, there is no uh, there's the value, the measured thickness is below 12 inches, then your reinforcement location is considered an other bar, and we get the corresponding factor to consider in your equation. So just to give you a note, why is it that for top bars it's greater? No? The factor of safety is greater because normally the concrete surrounding the top portion is weaker. Okay, we have a weaker concrete compared to the bottom portion, so we have a stronger concrete. Okay, so I'd like you to think about that. Okay, so why is it that there's a weaker concrete at the top portion rather than the bottom portion of your pit? Okay, for your coating factor psi e, we have to measure first the covering. Okay, so we have to measure the cover and the clear spacing. So we have to draw the, let's say we have here a bottom bar. So consider a bottom bar with two reinforcement. So what is the cover that we are talking about here? So we are talking about the distance from the edge of the bar up to the surface. Okay, so you call this a cover. Okay, C. You also have here a cover C. Okay, so if this is a C1, your side cover, you can place this as your C2, your bottom cover. And you also have a clear spacing, which is this one here, S. Okay, so the cover must, if the cover is less than 3 times the bar diameter and the clear spacing is 6 dB, then your factor for your psi e is automatically a 1.5. Okay, if there is an epoxy coating. For other epoxy coated bars or wires which does not satisfy the condition here on top, okay, then you use 1.2, and for uncoated reinforcement you use 1.0. So the factor of safety is bigger when you have a coating. Okay, these are coated, than compared to an uncoated reinforcement. By the way, why are you placing or applying a coating to the reinforcement? So the reason for that is you want it to be free from rust and corrosion, just in case you expose it to weather, okay, to extreme weather condition. But for normal conditions, you don't do it, because coating, application of coating means what? Additional cost. Okay. Okay. So for your psi t factor, by the way, take note that your psi t psi e must not exceed 1.7. In case your psi t multiplied by psi e exceed 1.7, then you use 1.7. Okay. If the product of this values, let's say 1.3 times 1.5 is greater than 1.7, then you use 1.7. Okay, so for your reinforcement size factor, so we are now dealing with the diameter of the bars. Okay, so we have here the diameter of the bar, dB. So if the diameter of the bar is number 6 and smaller, okay, number 6 is actually what? You still, do you know the American uh, standard on, so when we say number 3, 4, 5, 6, 7, 8, let's say 9, 10. So you just divide this by 8 to get your diameter. No? So you just this is in the unit. Okay. of American Standard Unit. Number 3 means 3 over 8 inch. Okay, so this is in inch. So this 4 over 8 is 1 half. Okay, so you always divide it by 8. So this 1 half, this is 5/8, this is 6/8 or 3/4. Okay, so this is 7/8, this is 1, this is 1 and 1/8. Okay, and this is 1 and 1/4. So you just convert this to millimeter approximately. Soft conversion will give you number 10 mm. Okay, so this is in millimeter. This is 10, 12, 16, 20, we have 22, 25, 28, and 32. Okay, so you still have number 11, etc. No, but these are the sizes that are commonly used. So for number 6 and smaller, so you have a 3/4 inch or 20 mm diameter. You use 0.8 for your reinforcement size factor. And for number 7 and larger, 7, 8, or 22 dB, you use 1.0 for your reinforcement size factor. By the way, this size here is not available in the Philippine standard. Okay, so these are ASTM standards. Okay, for your lightweight aggregate concrete factor, so normally we are using a normal aggregate concrete, but for in case we use the lightweight aggregate, so the aggregate, the coarse aggregate, the gravel is no longer an ordinary gravel stone that you get from the quarry. So you use 0.75 and 1 for normal aggregate, and 0.75 for lightweight aggregate. Or if FCT, this is the tensile strength of your concrete, not the steel. Okay, so this is tensile strength of lightweight concrete, lightweight aggregate concrete. So if FCT is specified, you use this formula. But this should not be less than, this should not be greater than 1. If it exceeds 1, you use 1.0. Okay, what's your CB again? So CB is the spacing or covering whichever is smaller. Okay, so remember the C1 and the C2 there. So you just place there C1, C2, S1, S2, and then you get this is equal to CB. Okay, CB is equal to this, whichever is smaller. No? So you measure all these values here, and then you compare and get the smallest. But take note here that the CB is actually a center to center, centered of the bar to the nearest concrete surface, and CB is 1/2 center to center spacing of the bar. Okay, the spacing or cover whichever is smaller. So we can Okay, readjust our drawing here. So let's just correct it. So this is spacing here is not at the surface. Okay, so this must be some at the space. Okay, at the center. Okay, at the center. So this must be at the center, and this must be also at the, okay, the center. Okay, and also your measurement of S must be S at the center. Okay, so since this is a 1/2, there's a 1/2 here, we have to divide this by uh, 2. Okay, so S1 over 2. Okay, so you get the smaller of this, and that will be your Cb. Okay, KTR is an index. It's a factor. It's a way on how to get rid of uh, the crack, okay, prediction. So it's a simple way of measuring if there is some danger in terms of splitting crack failure. And the formula for the ACI 2008 and the newer codes is actually 40 ATR over SN, wherein the FYT was removed. Okay, so by the way, this is again an English unit, while this is an SI unit here. Okay, so the English conversion of this old formula is actually ATR. I think, if I'm not mistaken, this is ATR FYT all over 1500 SN. Okay, so that is the English units of this. Anyway, when we use it in our problem, we'll be using SI. So your ATR is the total cross-sectional area of the transverse reinforcement. Take note that ATR shall be within the spacing S and crosses the potential plane of splitting. So I will show you what's meant by the potential plane of splitting when we solve the problem. Okay, S is the maximum transverse reinforcement within the length LD, and N is the number of wires or bars being developed along the plane of splitting. Also, ACI allows us to use a value of KTR is equal to 0 even if reinforcement is not present. Okay, note that Cb plus KTR must always be, all over dB must always be less than or equal to 2.5. Again, you cannot exceed the limit of 2.5 for this value of your C plus KTR. Okay, let's go now to some of the notes and general requirements on the application of development length in the bars. Okay. Okay, for the development of flexural reinforcement, the general requirements are we have to see to it that the LD requirement is checked on the critical sections. Okay, so we have to bear in mind that we need a check on this. And what are the critical sections? The critical sections are the points of maximum stress and the points where adjacent reinforcement terminates or is bent. Okay, so terminates or bent. Normally we do not bend it, so this is not no longer used nowadays, especially in the Philippines. What we do is we terminate or simply cut it. Okay, so cut or terminate. Okay, so if I have a beam, let's say here, and my bars are placed here. This is supposing a fix and beam. Let's say this is a fix and beam. Okay, so these are my reinforcement. So the critical sections are this one. No? Okay, so we have a maximum moment here. So somewhere here is a critical section. I have also a critical section here, and also a critical section at the midspan. Okay, because my moment diagram is actually like this. Okay, so they have a maximum moment here, and a maximum moment here, and a maximum moment here. Although only one is bigger, we have a big moment on this portion. Okay, so we have to check it on maximum stresses, and also we have to check it where there is a termination of the bar. Let's say I have a cut bar here. I place a bar that was cut there, and also a bar that was cut here. So supposing this is a continuous bar here, and this are continuous bars. Also, I have a cut bar here. So I have to check also this part as my critical section. This is also critical section. So I have to bear in mind that the critical sections defined in the development concept is at points of maximum stress and at points where the reinforcement is bent or cut. Okay? So for letter B, rebar shall extend beyond the point where it is no longer required a distance d or 12 dB, whichever is greater. So supposing this is my theoretical cutoff at this point, I have to extend it. Okay, I have to extend it at least a distance of d or 12 dB. So I cannot cut it theoretically at the point of inflection. So the theoretical cutoff point is normally at this point of inflection. Okay, the point of zero moment, the pi. Okay, so I cannot cut it here. So what I have to do is to extend it at least a distance d or 12 dB. What is that for? The reason for that is to provide factors of safety in case your moment diagram shifts from left to right or right to left due to the uh, unexpected loading conditions. Okay, so that's the reason for that. So for letter C, continuing reinforcement shall have an embedment length greater or equal to LD beyond the point where the terminated bar is no longer required to resist flexure. So again, we have to take note that this cut bar here have a continued reinforcement. So we have what you call here a cut bar, cut, and we have a continued bar. Okay, so this is a terminated bar and a continued bar. So the continuous bar or reinforcement should have an embedment length which is must be greater than the required length of development LD. Okay, so we have to check on this continued reinforcement. So bars may be terminated at the tension zone only if one of the following condition is satisfied. So we can also terminate bars class provided these three options will uh, be satisfied, but I don't want to confuse you on this. Might as well make your bar not to be terminated at the tension zone. So these are just for emergency cases where we cannot avoid bars to terminate at tension zones or to be cut at tension zones. So in case we can avoid it, I'll explain to you this in case we encounter it. I don't want you to be confused this time. Okay, so take note that here the reduction of the length of development is permitted for excess reinforcement except where anchorage or development of FY specifically required or the rebar is designed under provisions of 21.2.1.4 wherein MF is equal to AS required over AS provided. So this modification factor is actually a reduction factor if in case your required reinforcement is way beyond the provided reinforcement. Okay, so let's say the required reinforcement is only 2 bars and my provided reinforcement, my actual reinforcement is 4 bars. Then if I divide this 2 over 4, so my modification factor is now 0.50. Okay, so meaning to say my length of development can be reduced up to 50% because I have provided twice as much of the area of reinforcement required. So let's move on to some of the details shown by the ACI on how to terminate bars. Okay, so if I have here, so this is for continuous beams cut-off requirement. If I have here a continuous beam wherein reinforcement are already placed, okay, so what I'm going to do is to take note of my points of inflection. Okay, so my point of inflections are not fixed. Okay, it can move from this point up to this point here. Why? Because of the change in loadings. Okay, the dead load might change, the live load might change, the wind load might add up, the earthquake load might affect the beam, etc. Okay, so these points can move from left to right or from right to left. That's why you need to have a factor of safety on the extensions. And what is that factor of safety? The factor of safety of the movement of such, so let's consider here the moment curve on the negative reinforcement, which represents your top bars. Okay, so it can move up to a value of D or 12 dB when you cut it. You cannot cut it theoretically here at point where the moment is there at mx. You must cut it at the point wherein you have to extend it at least, okay, at least D or 12 dB for the what? For the terminated reinforcement. And you have to check also the length of development for the succeeding cutoff point. So this is the succeeding cutoff point. Okay, so this is the first cutoff point, this is the second cutoff point. So you have to check LD here up to there, extending beyond D or 12 dB, and also you have to check here up to there, extending also beyond D or 12 dB. Okay, so this is the extension. So this the cutoff point theoretically here is this one, and this is the extension. And the cutoff point theoretically here is this, and this is the extension. Okay, these are the extensions. Okay, so that's the way how to address the cutoff points. Also in your positive moment, so this positive moment refers to the bars here. Okay, so you start at the maximum positive, and then the theoretical cutoff point at a certain distance x is this one, but you have to extend it at least d or 12 dB there. Okay, so this is the extension. And then also you have to this is now the continuous bar, so you have to check whether this continuous bar has at least this LD requirement. Okay, so that is how to consider the cutting and terminating of bars for a continuous beam. Okay, for the bar size requirement and at simple supports and point of inflection, we have to check on the bar size by simply providing a factor of safety of 1.3, which is usable only if the reaction confines the ends of the reinforcement. Okay, so you need to check LA is the end of the anchorage length. So what is this length from the what's this? This is the support. Okay, so if the support up to there is given, so you have to check by adding this and this. So LA plus 1.3 mn over VU must be greater or equal to LD. Okay, so this is your LD here. Okay, and this is for simple support. Maximum size for bar A at point of inflections. Okay, so if I have a point of inflection just like this continuous beam here, I have also to check your LA plus, this time there's no longer the 1.3 factor over VU must be greater or equal to the LD requirement. Okay, so where's the point of inflection? If this is the moment diagram, okay, so if this is the point of inflection, this must be your moment diagram. So at the point of inflection, left to right, you have to check on LA plus Mn over VU greater than or equal to LD. Okay, so that's just a check, additional check. For the anchorage details, you have to take a look on the 90-degree bend for, what is this? This is the exterior support for a column normally. So you do not cut it there, you have to bend it 90 degrees. But have to check the hook. Okay, so you call this the LDH or the length of development of this hook. Okay, so this is a 90 degrees, or sometimes they also use a 180 degrees, but it's better to use a 90-degree hook. Exterior column. So anchorage to an adjacent beam, you just extend it. If you cannot make it continuous up to that point, at least this from this, there must be a check on the satisfaction of your LD requirement. So you don't need to bend it that way because you can still extend it because this is a continuous beam. Okay, this is an exterior column, but this is an interior support or a column. Okay, so take note of the extension, and this extension must be at least 1/3 of the reinforcement. If you have a reinforcement, three reinforcement here, 3 bars, you have to extend at least one. Okay, 1/3 of that. Okay, so these are just additional notes to give you a more holistic approach or understanding on length of development concepts. Okay, thank you very much. I'll address your concerns and questions uh, after this video.